The years since World War II have seen many dramatic changes in the way we live our lives. Few changes, though, have affected our world as much as the advances which have been made in aviation. From the days when the DC-3 was the workhorse of the fleet, to the first jet aircraft, to the modern fly-by-wire aircraft of today, the reliability and safety of air travel and the air transport system itself have been increasing at a steady rate. Unfortunately, the increase in safety and reliability of modern air travel has tended to obscure one basic fact. The consequence of failure in the air is final. Corrosion-related structural failures have contributed to serious air disasters in the past, and this will continue in the future unless you do your job identifying and removing corrosion on the aircraft placed in your care. This program, Corrosion 1, Corrosion Control for Aircraft, was specifically produced to prevent corrosion-related failures. The best way to do this is to make sure that you, the mechanic, know how to recognize, treat, and prevent corrosion. A challenging open book test on this program is available from your local FAA Flight Standards District office. The 25-question test is on the material covered in this program. With a score of 70% or higher, you will receive a certificate of training from the FAA. If you don't pass the first time, try again. We want to issue you the certificate. In your role as an aircraft mechanic or inspector, you are responsible for recognizing, preventing, and controlling corrosion on your aircraft. This program is based on FAA Advisory Circular AC 43-4A, Corrosion Control for Aircraft. You can get a free copy by writing the Superintendent of Documents, Washington, D.C. Keep it handy on the job and refer to it during inspections or when you encounter a particular problem with corrosion. Our program has 4 parts. Part 1 is an overview of corrosion basics. Part 2 looks at inspection requirements. Part 3 covers corrosion treatment. And Part 4 discusses preventive maintenance and corrosion-prone areas. Now, let's get started. In Part 1, we'll look at the various causes of corrosion, some of the more common electrolytes, and the types of corrosion you will typically see while maintaining your aircraft. Corrosion is a natural phenomenon. It attacks refined metals and alloys in an effort to return them to their original state. Corrosion can be thought of as an electrochemical process because a small amount of electrical current is also generated as the metals corrode. 4 conditions must always exist before corrosion can develop. There must be a metal that will corrode readily, called the anode. A different metal which has less tendency to corrode, called the cathode. An electrical path between the anode and the cathode, usually through metal-to-metal contact, and a conductive liquid called the electrolyte. A typical corrosion cell example that exists on your aircraft could have the aluminum skin as the anode, a steel fastener as the cathode, metal-to-metal contact as the electrical path, and rainwater, which may enter the small crevice between the skin and the fastener, as the electrolyte. Electrical current flows from the cathode to the anode through the electrical path, which, and here is the key, causes the loss of metal in the anode. Corrosion is like a cancer to an aircraft. Once it gets started, it will continue to spread without some preventive or corrective action. But remember, eliminating any one of the 4 conditions, anode, cathode, electrical path, or electrolyte, will stop or prevent corrosion. On the job, you need to know how different metals react with each other so you can spot potential trouble aboard your aircraft. The galvanic series chart, as shown here, shows how different metals compare with each other and how likely they are to corrode. The further apart 2 metals are on this chart, the faster one or the other will corrode if they are joined together. At the top of the chart are the metals which most easily corrode, such as magnesium and zinc. At the bottom are the metals which are the least likely to corrode, such as gold and platinum. Let's see how our example of the aluminum aircraft skin and stainless steel fastener looks on the galvanic series chart. Aluminum appears higher on the chart than stainless steel, which means that the aluminum will act as the anode and the stainless steel fastener as the cathode. This means that in a corrosive environment, there will be rapid corrosion of the aluminum skin where it contacts the stainless fasteners. On the other hand, if two metals are close to each other on the galvanic chart, corrosion will occur, but not as quickly. Other factors will also increase the corrosion of a metal. One factor is the relative size of the anodic and cathodic areas involved. If the cathode is small compared to the anode, corrosion will be slow. If the surface area of the cathode is large and the anode small, the corrosion process will be accelerated and the smaller anode will deteriorate quickly. Another factor is temperature. As the temperature increases, resistance to current flow in the electrolyte decreases. So you usually find more corrosion in tropical areas than you do in cold areas. Corrosion also increases with the time the metal is exposed to a corrosive environment. Another very important factor is the type of electrolyte. Let's take a look at electrolytes in greater detail. Electrolytes are one of the four basic factors which cause metals to corrode. Any moisture from condensation, humidity, rain, or even coffee would function as the electrolyte. The most common electrolytes are water, acids, and alkalis. Water is by far the most common electrolyte. Its corrosive effects, however, depend on the chemicals in the water. Tap water is less corrosive than rainwater because rainwater has a lower pH level, which indicates a higher acid content. Salt water is even more corrosive than rain due to its high salt content, which makes it a stronger electrolyte. Moderately strong acids will severely corrode most alloys used in aircraft construction. By far, the most destructive is battery acid. In addition, sulfuric acid found in volcanic dust, ozone from electrical discharges, and even human and animal waste, which contain uric acid, are very corrosive to metals. At the other end of the pH scale, alkalis aren't generally as harsh as acids, but will still attack aluminum and magnesium alloys. Alkaline chemical cleaners are particularly corrosive to aluminum. This program will now look at the types of corrosion you will come into contact with while maintaining aircraft. We will use their most commonly accepted names in describing each type of corrosion. They are uniform, pitting, galvanic, concentration cell, intergranular, exfoliation, filiform, stress corrosion cracking, corrosion fatigue, and fretting. Uniform corrosion, as the name suggests, attacks the metal uniformly over the entire surface. Uniform corrosion is commonly referred to as rust on steel surfaces. If it is allowed to continue, uniform corrosion will cause significant strength and weight loss to the metal. Pitting corrosion is the most common form of corrosion found on aluminum and magnesium alloys, but can also occur in other alloys. Pitting corrosion generally appears first as small white or gray dots, and in its more advanced stages, a white or gray powdery substance, similar to baby powder. Galvanic corrosion results from two different metals being in contact with each other in the presence of an electrolyte, like our steel fasteners and aluminum skin. Concentration cell, or crevice corrosion, occurs in areas where two metals are joined and moisture works its way into the crevice and sets up a corrosion cell. Intergranular corrosion is one of the most serious types of corrosion and can be likened to cancer in a human being. Once it starts at an exposed grain boundary, intergranular corrosion follows a specific path and eats out everything in its way along the grain boundary. Because it occurs below the surface, it can go a long time without detection. Metals have a clearly defined grain boundary, which differs chemically from the metal within the grain center. The grain boundary and grain center can react with each other as anode and cathode when in contact with an electrolyte. Exfoliation corrosion is an advanced form of intergranular corrosion. The surface grains of a metal are lifted up by the force of expanding corrosion products occurring at the grain boundaries just below the surface. Filiform corrosion begins at breaks in the paint and is recognized by its worm-like traces beneath the paint surface, which can lead to intergranular corrosion. Stress corrosion cracking is caused by a combination of stress and corrosion. It is an intergranular cracking of the metal in a specific environment. Corrosion fatigue is similar to stress corrosion cracking, but is caused by the combined effects of cyclic stress and corrosion. The pressurization and depressurization of aircraft during flight is a prime cause of fatigue. Even small amounts of corrosion on fatigued parts lowers the fatigue stress limit. This will allow a fracture to occur at a point far below normal fatigue limits. Fretting occurs when two surfaces are highly loaded and vibration causes them to rub against each other. This causes their protective coatings to be worn away, exposing the unprotected metals to the environment. Fretting is often identified by black streaks at the surface interface. To summarize Part 1, we discussed the basic theory of corrosion. We discussed factors that influence corrosion, including various electrolytes. And we reviewed the major types of corrosion which affect aircraft metals. For some, this was a review. For others, it was brand new material. We should all now have a solid foundation of corrosion knowledge to move to Part 2, inspection requirements. Part 2 will cover inspection requirements to include the basics of visual inspections, non-destructive inspections, NDI, and daily in-depth and special corrosion inspections. Good corrosion prevention and control practices start with thorough, regularly scheduled corrosion inspections. Detecting and treating corrosion early reduces costs, out-of-service time, and the possibility of corrosion-related accidents. Corrosion inspection is a continuing requirement and needs to be done daily. You should start all inspections with a thoroughly cleaned aircraft. Some of the inspection tools you will need are a good flashlight, an inspection mirror, a 5 to 10 power magnifying glass, a plastic scraper, and a felt tip marker to mark corroded areas. If you are going to do a good job inspecting your aircraft, you need to be able to recognize materials, proper coating, and damage which could lead to corrosion. This section is devoted to common aircraft metals, coatings, and their corrosion products. The primary metal used in manufacturing aircraft skin is aluminum alloy sheeting called Alclad, or simply clad. Although clad is highly resistant to corrosion, pitting can occur if inspection and routine maintenance are not performed. Other metals commonly used in aircraft construction require special preventive measures to protect them from corrosion. The information which follows summarizes Table 3-1 of your AC 43-4A. Magnesium is the most chemically active metal used in aircraft construction and is highly susceptible to pitting. Corrosion on magnesium initially appears as white spots on the metal, and with time, these spots can develop into white powdery mounds of corrosion product. Magnesium always requires a protective coating. It is usually painted and protected by either chemical conversion or electrolytic processes. Low alloy steels are vulnerable to surface oxidation, pitting, and intergranular corrosion. The reddish-brown product which is formed is rust, something which is easy to recognize. When corrosion attacks stainless steel, the surface darkens and becomes rough. Corrosive environments and industrial pollutants will cause corrosion on stainless. several metals are used to plate steels used in aircraft construction. Cadmium, for example, is a sacrificial coating. It corrodes, so the metal underneath doesn't. Cadmium is used to coat steel parts and to provide a compatible surface when a steel part is in contact with other materials. When the cadmium coating is intact, it will have a yellow appearance. When cadmium is worn away, exposing the metal underneath to the environment, a uniform reddish-brown stain often appears, which is the beginning of rust in the steel. Chromium is a protective coating which provides a smooth, wear-resistant surface that can be polished to a high luster. Chromium's continuous oxide coating protects not only itself, but the underlying metal as well. Even though very smooth, the surfaces of chromium coatings contain tiny cracks, which encourage pitting and will promote rusting of the steel underneath. Nickel plating is used for corrosion resistance, typically in a saltwater environment, and like chromium, the thickness of the coating determines the amount of protection which is given to the metal underneath. Non-destructive inspection, NDI, allows you to inspect for corrosion without doing damage to the aircraft itself. Several types of NDI are listed in your AC 43-4A, and we will discuss 6 of them. They are visual inspection, liquid dye penetrant, magnetic particle inspection, eddy current inspection, X-ray inspection, and ultrasonic inspection. We will look at each one briefly. With visual inspection, as the name implies, you use your eyes to detect damage on a surface which could indicate corrosion. By shining a flashlight at a low angle across the surface you are inspecting, any irregularities will produce shadows. This makes your job considerably easier. Additionally, feeling the surface with your hand can also help you detect corrosion. Visual inspection is the most widely used corrosion detection technique. The basic inspection tools mentioned earlier will help you find chipped, missing, and lifted paint, which could lead to corrosion of the metal underneath, dished and popped rivets, which means that the dissimilar metals have fallen victim to galvanic corrosion. Skin bulges or lifted surfaces, which mean that exfoliation or intergranular corrosion has begun, and cracks in the metal, which are a sign of stress corrosion cracking. Visual inspection, when done correctly, will help you detect the majority of corrosion types with a minimum of tools. The remaining NDI methods are only performed by qualified and certified NDI personnel. Each method has limitations and requires properly calibrated equipment. The liquid dye penetrant process can locate large stress corrosion or corrosion fatigue cracks on non-porous ferrous or non-ferrous metals. Dye is applied to the metal and enters the cracks. The dye is wiped off, and a developer is applied to the part which draws the dye to the surface. The area is then analyzed under a black light. This identifies any faults that might be present on the surface, and as shown by the quantity of dye remaining, will indicate the severity of the fault. The dye penetrant used in this technique must be completely removed, because if any is left behind, it will corrode the metal. Magnetic particle inspection is used for the detection of cracks or flaws on or near the surface of iron-based metals. The metal part is magnetized and tiny magnetic particles are applied to the object. Any surface faults will create high-intensity areas in the magnetic field. The magnetic particles will collect in these areas and pinpoint the location of the crack. Low-frequency eddy current inspection can be used to detect thinning in multi-layered structures due to corrosion and cracks. The inspection is performed by inducing eddy currents into a part and electronically observing variations in the induced field. The character of observed field change is interpreted to determine the nature of the defective condition. Eddy current is a good means for inspection because the inspection can be performed quickly with standard equipment and will obtain a high degree of sensitivity and reliability. X-ray inspections can detect moderate to severe corrosion or cracks within the metal. Like all NDI methods, X-ray inspections require a qualified and skilled operator to obtain reliable results. Ultrasonic testing will detect exfoliation, stress corrosion cracking, and general material thinning. Ultrasonic thickness gauges will detect moderate to severe damage after the corrosion products have been removed. Non-destructive inspection is a valuable tool in the fight against corrosion. NDI will allow you to make a measurable difference in your battle to stop corrosion. Regularly scheduled inspections are imperative to detect corrosion on your aircraft. There are generally 3 types of corrosion inspections which can be accomplished on your aircraft: daily or pre-flight inspections, routine corrosion inspections, and special corrosion inspections. During each type of inspection, you will be looking for visible signs of corrosion or corrosion products, specifically chipped or missing paint, which is exposing bare metal to the environment; bubbles in the paint, which may indicate corrosion has formed on the metal underneath; and excessive moisture or standing pools of water. As repetitive as they may become, the importance of daily and pre-flight inspections should never be forgotten. For daily and pre-flight inspections, always check engine compartments and the skin of the aircraft for missing or damaged paint and corrosion. Check all intake vents and engine frontal areas. Pay particular attention to exhaust trail areas, which are extremely corrosion prone. Potential trouble spots such as bilges, wheel and wheel wells, battery compartments, and fuel cell and cavity drains are some of the areas that should be given special attention for signs of corrosion. Routine corrosion inspections are performed at times when other maintenance activities have made accessible areas of the aircraft which are not normally accessible during daily or pre-flight inspections. Routine corrosion inspections require the removal of panels, access plates, and removable skin panels to thoroughly inspect the internal portions of the aircraft. Detailed corrosion checks should be accomplished while access plates are removed and components are disconnected or out of the way. Inspect corrosion-prone areas, such as around laboratories, in galleys, under floors, and in avionics, electronics, and baggage compartments. Pay particular attention to the paint coatings and make sure they are still intact. You should also examine areas where heavy grease coatings are used as preservatives. If the coating is in question, remove it and inspect the area underneath. Special corrosion inspections are required at each overhaul, routine inspection, or when required by an airworthiness directive or recommended by a manufacturer. When corrosion is found, the quality control inspector makes an evaluation to determine the extent and types of damage sustained, and then recommends a course of corrective action. The results of every corrosion inspection should then be recorded for later analysis. For extensive corrosion damage, a service difficulty or M/D report should be forwarded to the local FAA Flight Standards District Office for later analysis. If you are finding abnormal amounts of corrosion on your aircraft, your previous inspection or preventive maintenance program obviously did not do the job. Since you are the one who is most in tune with your aircraft's physical condition and operating schedule, you are most qualified to revise your corrosion program. Take the initiative to make your corrosion program one which remedies the deficiencies of your current program. But don't stop there. Address every problem your aircraft has been having and any others you think may occur in the future. An improved corrosion program will reduce both the seriousness and number of incidents of corrosion damage your aircraft sustains. Let's summarize Part 2. We discussed the proper tools you will need to conduct an effective inspection. We showed you how to detect the telltale signs of corrosion on common aircraft metals and paints, and what corrosion actually looks like. We briefly talked about 6 types of non-destructive inspections. And we went over the 3 kinds of corrosion inspections you should be performing on your aircraft. The material in this program has provided you with the basics you need to detect corrosion problems on your aircraft. Corrosion inspections are a key element in preventing the corrosion cancer from taking over your aircraft. By discovering corrosion problems early, you save repair time and the dollars which would have been spent unnecessarily. But most importantly, you are making your aircraft safer and more reliable. A major portion of your aircraft maintenance and inspection program involves the treatment of corrosion and corroded components. This part of our program will cover paint stripping, standard methods of corrosion removal, cleaning prior to inspection, corrosion assessment, and surface preparation. We will go over each step of the described corrosion treatment on steel and aluminum components. If you found traces of corrosion on a painted surface, you first have to remove all the paint in and around the corroded area to get to the corrosion. Paint removal from small areas is usually accomplished by mechanical abrasion or hand sanding. Chemical paint strippers are used on larger areas and should be handled with caution. Whenever you are working with chemical paint removers, check the label or material safety data sheet for any special manufacturer's instructions you may have to follow. Wear protective goggles and rubber gloves and protect your skin from accidental splashes. Do not use chemicals of any sort in small, unventilated areas, and always wear a respirator when directed by the manufacturer's instructions. Do not use paint removers containing acid on aircraft surfaces. Instead, use phenolic and non-phenolic paint removers. You should be aware that there are numerous environmental laws and regulations which may restrict the use of these products. Check to see if there are any EPA requirements which apply to your location, and be sure to follow all safety precautions. Before applying paint remover, be sure to mask surrounding areas which may be damaged by the stripper. These areas include windows and canopies, all plastic parts, rubber hoses and tires, and all composite surfaces. Apply a thick continuous coating of the paint remover and leave it there long enough to wrinkle and completely lift the paint. Scrapers, pads, or brushes can be used to remove stubborn paint. Use more paint remover as needed. Once the paint and stripper are removed, you can begin repairing the damage that corrosion has caused. First, you must remove all of the corrosion product and damaged metal. The corrosion removal procedure will be different for each metal or component, but this video will provide you with a good working foundation. Refer to AC 43-4A for material or component specifics. The primary methods of corrosion removal used in the field are mechanical. Mechanical corrosion removal is done either by hand or with handheld power tools. Hand sanding uses abrasive mat, abrasive paper, or metal wool and is suitable for small areas. Powered mechanical sanding, grinding, and buffing use abrasive mats, grinding wheels, sanding discs, or abrasive rubber mats. Abrasive blasting is the most thorough method for removing rust from both low alloy steel and high-stress steel surfaces on the aircraft exterior. It's important to remember that the smallest amount of rusting on a highly stressed steel part is potentially dangerous. The rust should be removed and controlled to prevent possible catastrophic failure of the part. Additionally, any surface abrasions or changes in surface structure from overheating can cause sudden failure of these parts. It is essential then that steel surfaces not be overheated during corrosion removal. When all the corrosion is removed, remove any residual paint, paint remover, and corrosion products by washing the surface with fresh water using a nylon bristle brush. Then remove any masking material and wash the entire aircraft or component with cleaning compound. The cleaning compound should be mixed to the manufacturer's recommended dilution. When finished, rinse the area again with fresh water to remove the cleaning compound. Be sure to remove all stripping compound from any nooks and crannies on the aircraft, because the stripper will adhere to the surface and start new corrosion. Corrosion damage assessment is required to determine whether the necessary repair and rework is within the limits set by the manufacturer. The first step in assessing corrosion damage is to classify the corrosion as light, moderate, or severe. Let's look at corrosion assessment of aluminum. Light corrosion is distinguished by discoloration or pitting to a maximum depth of 1/1000th of an inch. This is about 1/4 the thickness of an ordinary sheet of copier paper. Light corrosion can normally be removed by hand sanding. Moderate corrosion is characterized by blisters or evidence of scaling and flaking. Depths of pitting may be as deep as 1/100th of an inch and may require extensive mechanical sanding to repair. Severe corrosion is indicated by blistering, exfoliation, as well as scaling and flaking. Pitting depths will be greater than 1/100th of an inch. The manufacturer's repair manual will give the maximum amount of material which can be safely removed from a part or panel. If not, contact the aircraft manufacturer. You can use a depth dial gauge to measure the depth of the corroded areas. To properly use this tool, you will need to take readings both in and around the corroded area. First, you must zero the gauge by measuring a non-damaged area. Then take a reading from the deepest pit. This reading represents the amount of material lost to corrosion. Now that you have measured the extent of the corrosion damage, you must compare this last figure with the manufacturer's predetermined acceptable rework limits. If the damage exceeds the limit set by the aircraft manufacturer, the affected parts must be replaced. On large structural parts, where the corrosion damage exceeds what is allowed in the structural repair manual and replacement isn't practical, contact the aircraft manufacturer. Corrosion damage not outlined in the aircraft structural repair manual will require FAA engineering or manufacturer's data to repair the component. Once you have made the determination that the damage is within the manufacturer's rework limits, you must treat the surface to prepare for repainting. Each metal used in aircraft construction requires a different type of treatment prior to refinishing. Here we will look at aluminum, but full details for each metal are in your AC 43-4A. Many non-clad aluminum alloys used in aircraft are anodized prior to construction. Anodizing creates an aluminum oxide surface barrier which is naturally protective, adding to the alloy's natural oxide film. You must restore the anodizing coating to reworked surfaces. After cleaning, a chemical conversion coating such as chromic acid or allodyne should be applied to inhibit corrosion and provide a suitable surface for painting. Mix the conversion coating according to the manufacturer's instructions. Apply to the surface with a stiff bristle or paintbrush. Quickly rinse the area with water to neutralize the solution and stop the reaction process. Repaint the treated area with the paint mentioned in the manufacturer's specifications. This should include an epoxy primer and top coat system. Magnesium, like aluminum, requires a chemical conversion coating prior to painting. The most common conversion coating is Dow 19. If Dow 19 is not available, the conversion coating can be made by mixing chromium trioxide or nitric acid and sodium dichromate in distilled water. Consult the manufacturer's instructions or your AC 43-4A for precise mixing instructions. To summarize Part 3, we addressed every aspect of treating or repairing corroded metal. We discussed paint removal, removal of the corrosion product, corrosion damage assessment and rework limits, and surface preparation prior to painting. Each of the steps in the repair process must be done in turn, or the repair will not be airworthy. Preventive maintenance is perhaps the most significant activity you can accomplish in the war against corrosion. To keep your aircraft corrosion-free, you must have a detailed corrosion program to detect and remove existing corrosion and properly treat aircraft to prevent corrosion attack in the future. This section of the presentation will go over 10 key steps of a good preventive maintenance program and will give you the opportunity to test your newly acquired skills in corrosion detection on some of the more corrosion-prone areas found on aircraft. The first and perhaps most important requirement of any aircraft corrosion preventive maintenance program is to have mechanics who are well trained in the essentials of corrosion control. A well-trained mechanic is the best and most cost-effective defense against corrosion. The second step of the program is the establishment of regularly scheduled inspections. All the aircraft corrosion training in the world is ineffective without daily, routine, or special corrosion inspections. Thorough cleaning and application of corrosion prevention compounds on a regular basis is the third step in preventing corrosion on your aircraft. The aircraft kept outside should be cleaned at least once every month, or more frequently if located in a severe corrosion environment. Thorough lubrication and application of corrosion preventive compounds in conjunction with a detailed corrosion inspection should take place at least every 90 days. More inspections, as frequent as every 15 days, will be required in severe environments like those found near industrial or coastal areas. Several different cleaning compounds are available for use on your aircraft. For general aircraft cleaning, moderately alkaline cleaners with pH between 7.5 and 10 are recommended. Specialized cleaners can be used for other purposes. Please refer to AC 43-4A for these cleaners. Corrosion preventive compounds are used to protect metal aircraft parts and components from corrosion. These compounds work in two ways: by eliminating the metal-to-metal contact and by displacing water or other contaminants from the surface, thereby eliminating the electrolyte. Step 4 is treatment. It is extremely important to take care of corrosion problems as soon as they are discovered. A delay in proper treatment will only allow the corrosion process to continue and will cost you more man-hours and more money to repair. Always treat corrosion promptly upon detection. Step 5 is utilization of the proper tools, equipment, and materials while performing your corrosion duties. This equipment includes the inspection tools we discussed earlier and safety equipment like goggles and masks that are important for personal protection. Finally, it is important to use the proper abrasives, chemical conversion coatings, and cleaners when treating or preventing corrosion. Step 6, inspection of damaged paint, including making sure the paint finish remains intact, is a key requirement in preventing corrosion on your aircraft. The paint system protects the metal from contact with the environment and oftentimes from contact with dissimilar metals. Nicks, scratches, and other damage to paint systems are often the starting point for corrosion. While performing maintenance and other activities around your aircraft, be careful not to damage the paint. Be sure to repaint when damage is found. Step 7 is the elimination of blocked drain holes and passages which allow water and other contaminants to accumulate unnecessarily. This will break down any coating system and will rapidly lead to corrosion. Make sure that all drains remain open and functional, and that no debris is blocking their path. Step 8 is inspection of gaskets and sealants. Gaskets and sealants are often used in aircraft construction to prevent the entry of water. If you spot any damaged or deteriorated gaskets or sealants on your aircraft, replace them at once to prevent water intrusion into corrosion-prone areas. Step 9 is to minimize the amount of time your aircraft is exposed to adverse environments if at all possible. This is perhaps the best way to prevent corrosion. If you have access to a hangar, use it. Step 10 may be a mundane paperwork-filled task, but it is very important when it comes to keeping your aircraft corrosion-free. You must keep accurate records of corrosion inspections, repairs, and any deficiencies you discover. Take photos to attach to reports. You must also report any material or design deficiencies to the aircraft manufacturer and notify the FAA so that corrective action may be taken if required. Fill out a malfunction or defect report for Part 91 aircraft or a service difficulty report for Part 121 or 135 aircraft. The FAA uses this information to publish AC 43-16, Aviation Alerts. You should also report design deficiencies, which could include anything from an uncoated part that corrodes readily to a design which allows water to collect, creating a corrosion hazard. We're telling you all this because corrosion is a very serious business. Bottom line, corrosion is your business. Remember the opening of the program and the damage caused by corrosion. Ignoring a small fatigue crack caused by corrosion might not seem important at the time, but how would you feel if your aircraft crashed because of a failure that you could have prevented? By following this 10-step preventive maintenance program, you will have the jump on corrosion, and you will save time, valuable time, and money. You will also be heading off potential disaster. Now it is time to put your corrosion knowledge to the test. Up to this point, we have tried to provide you with the basic building blocks and a firm foundation of corrosion background information. We will show you a picture of a major aircraft component or area. Then we will ask you certain corrosion-related questions. This quiz will make you sharper on corrosion. The areas we will focus on are some of the most corrosion-prone areas of your aircraft. Okay, let's get started. This is a typical exhaust trail area from an aircraft. Where is corrosion likely to occur, and what can be done to stop it? Because both jet and reciprocating engine exhaust gas deposits are very corrosive, exhaust trail areas should be cleaned daily. Also check for paint blisters and chipped or missing paint. Inspection and maintenance of exhaust trail areas should include attention to gaps, seams, hinges, and fairings which are located near the exhaust path. You should remove fairings and access plates whenever possible. Shown here is an aircraft battery compartment. Why is this a particularly troublesome corrosion-prone area? And what can you do to prevent corrosion there? As discussed earlier, aircraft batteries use an electrochemical process to generate energy, and this requires an electrolyte. Fumes from an overheated battery are difficult to contain and will spread to the internal structure, attacking any unprotected surfaces. Frequent cleaning of the battery compartment and neutralization of the electrolyte will minimize corrosion. Also, you can spray a corrosion preventive compound on surfaces within the compartment to provide extra protection. If there are external battery vent openings in the aircraft skin, they should be included in inspection and maintenance procedures. Why is the bilge area such a corrosion problem, and what can you do to stop it? The bilge area is a common trouble spot in all aircraft since it collects waste fluids, water, and other debris which can set up a corrosion cell. Keeping bilge areas dry is the best way to protect against corrosion. Corrosion preventive compounds can also be applied to these areas. What causes laboratories and galleys to be such corrosion trouble spots, and can you do anything about it? Spills and leaks in galleys and laboratories, particularly the deck under laboratories, sinks, and ranges, are what makes these areas so troublesome. You can't be there on every flight to prevent every spill, but you can pay special attention to these areas during routine maintenance. Clean them frequently in order to maintain their protective sealants and paint finishes. Frequently inspect bilge areas under laboratories and galleys. The same can be said for cargo areas. Damage caused by spills and residue from cargo can undermine the structural integrity of the aircraft. The wheel well area, probably receives more punishment than any other area of the aircraft. It is subject to mud, water, salt, gravel, and other flying debris during flight operations, all of which can contribute to corrosion. Can you identify the areas most subject to corrosion and explain why? There are many trouble spots in the wheel well and landing gear area which should be examined closely during inspections. All high-strength steel surfaces which are subject to corrosion fatigue, all exposed surfaces of struts, oleos, arms, and hardware, much of which is unpainted, exposed electrical equipment, axle interiors, and any crevices between stiffeners, ribs, and lower skin which trap water and other debris, magnesium wheels and bolts, where you may have dissimilar metal contact and exposed rigid tubing, especially under clamps and identification tape. The key to preventing corrosion on landing gear is frequent cleaning and lubrication of components. Refer to Figure 4-3 in your AC 43-4A to view the landing gear and wheel corrosion points in detail. External aircraft skin surfaces are readily visible, and maintenance and inspection procedures for them are well established. There are several problem areas that you must be able to recognize and treat right away to prevent the cancer-like spread of corrosion. The corrosion is easy to spot around the head of this rivet. But what caused this problem, and what could have been done to prevent it? This corrosion was caused by a breakdown in the paint film that shielded the metal from the environment. When the paint cracked, an electrolyte was allowed to enter the area and set up a corrosion cell between the steel fastener and aluminum skin. Whenever cracks or breaks in the painting system are discovered, they must be touched up as soon as possible to prevent corrosion. Moisture and corrosive agent intrusion also cause corrosion in the seams and joints of fairing surfaces. Any cracking or chipping of the paint coating around seams or crevices must be touched up immediately. Aside from visual inspection, is there any other way to detect corrosion on aircraft skin? Corrosion attack is usually detectable by a bulging of the skin surface, which often enables you to feel bubbles by running over the surface of the skin lightly with your hands. In addition, NDI procedures such as eddy current can be used to detect thinning skin or cracks in aircraft skin. Piano-type hinges used on access doors or plates tend to be a serious corrosion-prone area. Why is this so? And what can be done to stop it? Piano hinges are prime spots for corrosion due to contact between the steel pin and the aluminum hinge. They are also natural traps for dirt, salt, and moisture. Rarely used hinges will often corrode and freeze closed. To prevent this, they should be cleaned and lubricated during each inspection. Where is corrosion likely to occur on the engine? Engine frontal areas and cooling air vents are routinely exposed to airborne dirt and dust, runway gravel, and rain. Engine accessory mounting bases may have small areas of unpainted aluminum or magnesium on the machined mounting surfaces. This makes them prime targets for corrosion. Inspect all sections of the cooling air path completely. Pay special attention to obstructions and crevices where salt deposits may build up during marine operations. Although we only touched on corrosion problems of avionics briefly in this program, what do you think the main differences are between airframe and avionics corrosion control? There are three main differences which make avionics corrosion control so difficult. Number one, less durable corrosion protection systems are used on avionics. Second, Active and dissimilar metals are often left unprotected and in electrical contact. And finally, even a small amount of corrosion can make equipment inoperable. For more information on avionics corrosion, consult AC 43-4A, Chapter 4. Electrical connectors can be a particular corrosion problem due to moisture collection. To summarize, Part 4 dealt with preventive maintenance. First, we talked about the 10 necessary steps in a proper corrosion preventive maintenance program. Then we went over some of the worst corrosion problem areas on aircraft and gave you ways to prevent corrosion in these areas. At the same time, we gave you a chance to test your corrosion knowledge. At the risk of being repetitive, let us tell you one more time how important performing good preventive maintenance is in trying to control corrosion. If you take one idea with you from this presentation, let it be this: preventive maintenance is the single most important thing you can do to control the cancer of corrosion on your aircraft. We know that corrosion is not a glamorous subject, and there are other items you must attend to on your aircraft. Despite your busy schedule, corrosion preventive maintenance should remain a top priority. The few minutes you spend inspecting components, washing the aircraft, unclogging drain holes, touching up paint jobs, or applying corrosion preventive compounds will save you hours upon hours of costly component or structural repair. We have provided you with a lot of information during the past few minutes to give you a good foundation of knowledge of corrosion maintenance and prevention. Constant learning and education is a part of being a professional, and we strongly encourage you to read the AC 43-4A and other corrosion information to build on this knowledge base. We hope that this increased awareness will make you a better mechanic or technician, and that we have impressed upon you the consequences of ignoring corrosion on your aircraft. In Part 1, we took a look at the corrosion process and the elements required for corrosion to occur. In Part 2, we showed you what forms corrosion can take on your aircraft and introduced basic corrosion inspection techniques to help you spot corrosion problems early before you have a catastrophic failure. In Part 3, we went over the procedures for treating corrosion and repairing the component or structure. And finally, in Part 4, we discussed the basics of a corrosion preventive maintenance program and focused attention on some traditional aircraft corrosion-prone areas. Be sure to get a copy of AC 43-4A, which contains the majority of the information presented to you in this videotape, and use it as part of your corrosion control program. Remember, the FAA Flight Standard Service Back to Basics 2 program offers a certificate of training for all mechanics who pass the 25-question written exam. We once again encourage you to take this test and receive your Corrosion 1 Corrosion Control for Aircraft certification. Thank you for your attention, and remember that the well-trained and conscientious mechanic or inspector can play an active role in making air travel safer and more reliable by eliminating corrosion.
In the hectic, fast-paced, and high-pressure world of running a commuter airline, many operators overlook the problem of corrosion. But corrosion is like a cancer. quietly eating away at aircraft components and structural elements, and also eating away at your profits. And like cancer, once corrosion gets started, it will spread unless some preventive or corrective action is taken. Corrosion isn't particular. It will devastate both large and small aircraft. In light of the 1988 Aloha incident in Hawaii, more and more major carriers have implemented corrosion programs to combat the effects of environmental and stress-related corrosion. The benefits of such programs haven't taken long to be felt on the bottom line. Corrosion programs have been proven to save on maintenance costs over the life of an aircraft. Corrosion prevention programs of the major airlines have been shown to improve safety, save money on the cost of replacement parts, reduce labor cost in replacing corroded components, limit lost revenues from aircraft downtime, extend aircraft life, and increase aircraft resale value. A corrosion control program can have these same benefits for commuter airlines. This video is the second in a series relating to corrosion prevention and corrosion control on commercial aircraft. The first was titled Corrosion 1, Corrosion Control for Aircraft. The FAA video Corrosion 1 took an in-depth look at corrosion and how to prevent and treat it. In Corrosion 2, we'll start with a review of corrosion and basic prevention techniques, but more importantly, we'll provide you with the basics of how to set up a corrosion program for your airline. If you have corrosion prevention programs which have been designed by your aircraft manufacturer, we strongly encourage you to follow them. The same elements and operating stresses that plague the large aircraft of the major air carriers also affect commuter aircraft. Therefore, commuter airlines should have corrosion control programs in place similar to those already established by major air carriers. The very nature of commuter airline operations subjects your aircraft to more corrosive environments than the larger aircraft. This is because commuter aircraft generally fly at altitudes lower than 20,000 feet, which exposes them for longer periods of time to the worst operating environments, from acid rain to saltwater spray. Also, due to the shorter flights and longer utilization times of commuter aircraft, they generally go through more operating cycles than a major carrier, which contributes to corrosion fatigue. To compound these issues, there are presently few manufacturers' corrosion control programs, and there are even fewer corrosion control programs mandated by airworthiness directives. As we mentioned before, aircraft corrosion isn't passive. It's attacking your fleet right now. And with each passing day, corrosion progresses a little further, which makes your aircraft less tolerant to fatigue and wear damage. It should be noted that not only can your aircraft structure be eaten away, thinned by a corrosive environment, but its tolerance to fatigue cracks can be reduced. That is, a cracked structure exposed to a corrosive environment has a greater potential for sudden failure. Now we'll briefly review the basics of corrosion, provide you with the tools you'll need to set up a corrosion program for your fleet, and step through the establishment of a sample corrosion program. Corrosion is the process of refined metal trying to return to its natural state, metal ore. 4 basic factors are needed for corrosion to occur. Eliminating any one of the 4 corrosion-causing factors, the anode, the cathode, the electrical path, or the electrolyte, will stop or prevent corrosion. Stopping one or more of these factors can be accomplished by keeping the aircraft surfaces and components as clean as possible, regularly inspecting all surfaces, touching up any breaks in the paint, and frequently applying effective corrosion preventive compounds. Regularly scheduled maintenance and inspections are the key components of any effective corrosion prevention and control program. There are many types of corrosion that can affect your aircraft. They are described in detail in Corrosion 1, but quickly they are uniform, pitting, galvanic, concentration cell, intergranular, exfoliation, filiform, stress corrosion cracking, corrosion fatigue, and fretting. The types of corrosion, how to identify them, and how to treat them are well documented in AC 43-4A, Corrosion Control for Aircraft. We recommend your mechanics obtain a copy from the U.S. Government Printing Office and become familiar with it. We also recommend that you obtain a copy of the video Corrosion 1 and make it required viewing as a refresher for your mechanics. You can borrow a copy from your Flight Standards District Office. As you design your corrosion control program, you must consider individual needs, such as maintenance, flight schedules, and the composition of your fleet. This segment of the program will show you how to develop your corrosion program specific to your operation by reviewing 3 elements incorporated in all successful corrosion control programs. These elements are 1. Factors which influence corrosion rate, 2. Different corrosion levels, and 3. Corrosion-prone areas. This information will help you design and execute your own corrosion program. Corrosion is a process that occurs naturally over time, but there are several other factors which can accelerate or retard the rate of corrosion. These corrosion factors center around your aircraft design and operating environment. What, where, and how you fly will determine whether you need a very aggressive or a less aggressive corrosion maintenance program. Some basic design factors of each aircraft can influence the rate at which your aircraft corrodes. The following is a quick review of some design factors which will accelerate corrosion damage. Lap seams are natural water traps, which allow water to enter and collect in areas which were not designed to withstand such a corrosive environment. Clogged drainage holes will also lead to standing water. Another major area which can lead to increased corrosion is when 2 dissimilar metals are in contact with each other. When this situation arises, extra care must be taken at every maintenance interval to ensure these metals are protected from electrolytes. Typical of dissimilar metal contact is the case of stainless steel fasteners attached to aluminum skin. If dissimilar metals cannot be insulated from each other by paint or sealant, corrosion can only be prevented by carefully maintaining the integrity of the paint on both metals to eliminate electrolyte contact. This brings us to another factor to be considered in designing your corrosion control program: flawed paint. This can be anything from poorly applied or maintained paint schemes to nicks, scratches, and other flaws which occur during the operation or service of an aircraft. Areas prone to paint damage during operation, such as the wheel well and landing gear areas, should be checked regularly for chipped or missing paint. This and any other damage to the paint system should be repaired promptly with touch-up paint or an effective corrosion preventive compound. The second corrosion factor is the aircraft's operating environment and its effect on the rate of corrosion. For example, the closer your aircraft are to the seacoast or other source of moisture or salt-laden air, the faster your aircraft will tend to corrode. Areas with constant high levels of humidity, including the tropics, will accelerate the corrosion process. Operating in and out of industrial areas with high levels of airborne pollutants also accelerates corrosion. When operating in areas where these factors are prevalent, your corrosion control program must be far more aggressive than if these factors were absent. This may mean more frequent washing of the aircraft, as well as increased frequency of detailed corrosion inspections. Operating conditions can also create an increased corrosion potential on your aircraft. By operating conditions, we mean problems associated with routine use or misuse of the aircraft. These factors include any type of spillage, either of a chemical or of spills in the lavatory or galley areas of the aircraft, Both of these places are classic breeding grounds for corrosion. The cargo area is another area where operating conditions will dictate the level of corrosion protection required. You'll need a more aggressive corrosion control program if you carry any live animals or fresh or frozen seafood. If your aircraft are subject to these conditions, once again, your corrosion control program must be more aggressive than normal. Corrosion-resistant materials, high-tech paint schemes, and effective corrosion prevention compounds are useless unless you have trained, motivated mechanics prepared properly to address problems as they arise. Maintenance personnel must understand the causes of corrosion and how to treat it. With an effective corrosion control program in place, lack of corrosion awareness will not be a problem for your operation. In order to evaluate the condition of your aircraft fleet with respect to corrosion, you'll need some way to differentiate the different levels of corrosion attack. 3 levels of corrosion have been defined as they relate to aircraft. These levels do not dictate repair requirements. They are simply used to determine the actions required to prevent or control corrosion to an acceptable level between inspections. Level 1 corrosion is the least severe stage of corrosion. Level 1 corrosion is defined as local, generally light corrosion which can be blended out or reworked within the manufacturer's limits. Even if corrosion damage requires a repair which exceeds the manufacturer's limits, if this is a result of continuous light corrosion repairs, it should still be considered Level 1 corrosion. And finally, if local corrosion can be linked to a single unusual event, such as a fire or chemical spill, it should still be considered Level 1 corrosion. Level 2 corrosion is more serious than Level 1 corrosion. Level 2 corrosion is defined as corrosion occurring between successive inspections that requires rework or blend-out that exceeds manufacturer's limits. Level 2 corrosion can also be widespread, extending beyond one bay, which requires rework approaching manufacturer's limits. Level 3 corrosion is the most serious level of corrosion. If found during inspection, Level 3 corrosion requires expeditious action, since it affects the airworthiness and safety of the aircraft. Standardized corrosion levels are extremely important to any corrosion program. During initial inspections, they can be used to establish a benchmark and designate potential trouble spots. As the program continues, they can be used to measure the efficiency of the program by charting how well your prevention efforts are working. The final tool for your corrosion program is the identification of the corrosion-prone areas of the aircraft. The collective experience of the aircraft manufacturers and operators have identified the major corrosion-prone areas on aircraft. These areas were presented in the videotape Corrosion 1. To assist in developing a corrosion control program, the aircraft should be seen as having a primary structure and a secondary structure. The primary structure should be further subdivided into a category called Principal Structural Elements, or PSEs, and Non-Principal Primary Structure. Principal structural elements are those which are needed to assure continuing airworthiness and should be defined for each aircraft in your structural repair manual or manufacturer's service instructions. Examples of PSEs may include wing spars and skins, fuselage frames and skins, pressure bulkheads, and landing gear beams. Examples of non-principal primary structures may include elevators, rudders, ailerons, seat tracks, and windows. Examples of secondary structure components may include landing gear doors, aerodynamic fairings and support structure, and service panels such as lavatory and galley access panels. Use these designations in your corrosion control program to assign priority to maintenance actions and inspections. Depending on your individual circumstances, you may need to schedule more frequent inspections of the principal structural elements and for the other primary structure. We've just presented the fundamental tools needed to establish a corrosion control program for your airline. We'll now use these tools to establish a sample corrosion program. A simple three-step approach is used to devise and implement your corrosion program. Step 1. Conduct a baseline inspection of an aircraft to determine corrosion trouble spots. Step 2. Develop aircraft maps of corrosion trouble spots found during the baseline inspection. And Step 3. Incorporate inspections and effective treatment into existing maintenance schedules. To begin with, you must discover the extent of the existing corrosion problems of your fleet. To do this, you need to establish a baseline for each aircraft make and model you are operating. Theoretically, the oldest aircraft in your fleet will have the most severe corrosion problems, but this isn't always the case. Examine the service history of your aircraft and determine which aircraft of each make and model has been subjected to the most corrosive environment. Then select the aircraft which is the most likely candidate as the baseline. But be careful when selecting this baseline aircraft. For example, let's say you have 10 -7 aircraft in your fleet, with the oldest being 12 years old and the others between 8 and 10 years old. If you pick the older aircraft based solely on age instead of operating history, you may find little corrosion. That 12-year-old aircraft may have been recently purchased from an airline which flew only from Albuquerque to Phoenix, while the others may have spent their entire operating life in the Aleutians. Prior to the initial baseline inspection, develop a checklist for all of your aircraft makes and models. This checklist should include all primary and secondary structural elements. In addition, include any areas or structures which have proven to be corrosion trouble spots on the aircraft. Some of the more common areas are battery compartments, avionics bays, exhaust trail areas, galleys, lavatories, and structures around the potable water container. During your baseline inspection, be sure to note items such as dissimilar metal contact and areas of poor drainage as potential trouble spots, and plan more frequent inspections of these areas. To establish a baseline, first inspect the entire aircraft to determine the location of any corroded areas. At the same time, determine the severity of damage. Ideally, the baseline inspection should take place in conjunction with a heavy inspection or aircraft overhaul. This will allow access to all areas which are not accessible at any other time. The baseline inspection should be extensive enough not to miss any potential trouble spot. At a minimum, the primary and secondary structural elements listed in the previous section should be thoroughly inspected and evaluated for corrosion. If no corrosion is found during the baseline inspection, note this on the form by placing a 0 next to the component. This clearly indicates that this area is not a corrosion trouble spot. However, this doesn't mean that it should be ignored in future inspections. If corrosion is found in an area during the baseline inspection, the mechanic must determine the extent of the corrosion. The next step in your program is to map the results of the baseline inspections to record the aircraft trouble spots. These aircraft maps will help the maintenance department to design aircraft inspection programs. Shown here is a sample of such a map from a larger air carrier corrosion control program. This map will be used as a guide during all subsequent inspections and scheduled maintenance activity. This guide should indicate the inspection frequency and any treatment or prevention actions to be accomplished during scheduled maintenance. The guide should also indicate the number of times a month the aircraft should be washed based upon the corrosion potential of the aircraft in operation. AC 43-4A gives guidance on the washing frequency based on your operating location. Now that you've developed a corrosion map, you're ready to incorporate your findings into your fleet's continuous airworthiness maintenance or inspection program. In order to put your corrosion control program together, you must consider your maintenance schedule. This is as important as it is practical. You want to devise an effective corrosion control program which won't disrupt normal maintenance. In a perfect world, corrosion control would be easy, with an unlimited budget and unlimited time for maintenance. But in the real world, limited resources require you to analyze your maintenance needs and determine when and how effective corrosion prevention techniques can be employed. From this point, we recommend you institute corrosion control into the following 4 elements: daily inspection and cleaning, scheduled and non-scheduled maintenance, evaluation of program effectiveness, and feedback to FAA, manufacturers, and fellow operators. Areas which the baseline inspections have proven to experience no corrosion should not appear on the map, and therefore will not be the subject of daily inspections. If moderate or severe corrosion was discovered during the baseline inspection, there's a corrosion problem. These areas should be inspected carefully during daily inspections of all fleet aircraft of that type, and the problem should be addressed. If the component is accessible during each daily inspection, the mechanic should visually inspect the area for corrosion or factors which may cause corrosion. Any corrosion found should be written up. The level of corrosion should be defined, and action should be taken. All trouble spots should be kept as clean and as dry as possible. During daily inspections, all drainage paths should be checked and cleared, and standing water should be removed from the aircraft. A well-planned corrosion control and prevention program should cause little disruption of current daily maintenance routines. Whenever an aircraft is down for a longer period of time to perform maintenance, your mechanic should take the opportunity to implement corrosion prevention activities. Perform more extensive visual inspections on those areas which you have identified as corrosion prone. Consider using non-destructive test methods, such as eddy current if they are available. They will more than pay back the cost of the equipment. Extended periods of maintenance are also an excellent time to repair any corrosion damage found and perform prevention activities such as touch-up of damaged paint. During this maintenance interval, your mechanic should also apply effective corrosion preventive compound, or CPC, to the identified corrosion-prone areas. Routine use of corrosion preventive compounds should be encouraged for areas which are corrosion-prone or where paint has been damaged until a more permanent treatment can be applied. Daily and scheduled maintenance offer ample opportunity to inject corrosion prevention into your operations maintenance philosophy. As this corrosion control program becomes part of your company culture, it will yield dollar savings in parts and labor hours, decreased downtime, and increased level of safety to the traveling public. You may want to consider expanding your corrosion control program to some corrosion-prone components, such as the engines and propellers and avionics connectors. Corrosion on these components should not be ignored, and paying attention to corrosion on these areas will also yield significant benefits for your airline. A good time to evaluate the effectiveness of your corrosion control program is during heavy inspections. During these heavy inspection periods, an inspection similar to the baseline inspection should be performed, which utilizes the original aircraft checklist of potential problem areas. If there are no reports of corrosion during these inspections, then you can be encouraged that your corrosion program is effective. If, however, you discover any serious corrosion on these subsequent inspections, the corrosion program must be revised to eliminate the deficiencies. Revisions to the program should include the addition of any new corrosion trouble spots to the corrosion maps. Your corrosion program should have uncovered some corrosion-prone areas on your aircraft. Some of your aircraft may have some of the design deficiencies discussed earlier, which have served to accelerate corrosion rates. It's very important that you alert the manufacturers and the FAA of any corrosion problems through the use of service difficulty reports. Manufacturers need to be notified of corrosion problems so they can solve these problems. Manufacturers of larger aircraft, in concert with the airlines, have corrected many design problems and, not coincidentally, instituted very effective corrosion control programs. The corrosion program, which we have outlined here, is simple and easy to implement, but will lead to maintenance cost savings in both the short and the long term. We realize that additional maintenance for corrosion control will cost some dollars to implement, but the benefits far outweigh this added expenditure. Replacing corroded components is also expensive from a labor standpoint. It consumes valuable labor hours to replace these components and usually results in extended downtime and unbudgeted expense. An effective corrosion control program will actually save labor hours in the long run, which will translate to increased revenues and lower costs. These cost savings, combined with the added benefits of increased aircraft availability, improved reliability and safety, and better public relations, make it an easy decision for you to develop and implement a corrosion control program for your commuter airline.